So, an interesting question that we might ask is, what is the function that is computed here? So I told you we're gonna be with this recursion for a while. What is the function that is computed here? Okay, so what is the function computed? So we think and look and think, walking up and down, walking up and down, walking up and down. No! It's not the way you answer questions like this. The way you answer questions like this is you must first start by tinkering. Okay. So let's compute f of n for different values of n. So n, f of n. So when n equals 0, it's 0. Okay. When n equals 1, it's f of 0 plus 1, so it's 1. And if n equals 2, it's f of 1 plus 3, so that's 4. When n equals 3, it's f of 2 plus 2 times 3 plus 5, plus 2 times 3 minus 1, which is 5. So 4 plus 5, 9. When n equals 4, it's going to give you f of 3, which is 9, plus 2 times 4 minus 1, that's 7. So 7 plus 9, 16. Anybody have a guess for f of 5? Well, let's do it. Let's compute it. Okay, so f of 5, I'll plug in, I want f of 5, f of 4, so that's 16, plus 9. 10 minus 1 is 9, so 16 plus 9, 25. Anybody have a guess for f of 6? F of 6, ta-da! You might think squares. Okay, so let's guess 36. Well, we could go and verify. Okay, but at this point, we're ready to sort of make a guess. 36. Okay. Let me show you one way to sort of get a formula for f of n. Okay, so a formula. So here we're ready to make a guess. But in a more general setting, if the guess is not obvious, we might try to derive a formula for f of n. Okay, and sometimes this is called unfolding the recursion. You unfolding the recursion to get a formula. Okay. Again, it's just a heuristic way to derive a formula. Okay. And here's how it goes. Well, I'm interested in a formula for f of n. So I'm interested in a formula for f of n. So I have f of n here. Okay. And what do I know? I know that f of n is equal to, f of n minus 1 plus 2n minus 1. And now you say, well, I need f of n minus 1, so I'll write that here. F of n minus 1 is what is equal to, according to the same recursion, f of n minus 2 plus, okay, now 2 times n minus 1, so I'm going to plug in, instead of n here, I'm going to plug in n minus 1, so 2 times n minus 1 minus 1, so that's 2n minus 3. Okay, but I need f of n minus 2. I don't seem to be making any progress. I need f of n minus 2, which is f of n minus 3, plus 2n minus 5. Because if I plug in n minus 2 into here, I get, 2 times n minus 2 is 2n minus 4, minus 1 is 2n minus 5. I don't seem to be getting any progress, except that each time the number here is dropping by 2. Okay, so, now I'm going to do the dot, dot, dot thing, which is now where the monkey business is cropping into this analysis. So dot, dot, dot. Okay, so f of 2 is going to equal f of 1 plus 3, and f of 1 is going to equal f of 0 plus 1, and then f of 0 is going to equal it's just going to equal 0. Okay, so I don't seem to have gained anything. I just inflated my board with a whole bunch of what look like useless equations, except that you observe that, f of n minus 1 appears here and here, f of n minus 2 here, here, 3 here, here, and so on. 1 here, here, 0 here, here. Okay, so, and now a fundamental fact from algebra, if I add everything on the left-hand side, I should add everything on the right-hand side. So, add add. So if I add here, it's got to equal the addition of these guys. Okay. But when I add all these guys and equate it to the sum of all these guys, look, the f of 0 will cancel the f of 0 on this side, because I'm now adding, so I'll have f of 0 on both sides. Cancel. Okay, the f of 1 will cancel the f of 1. The f of 2 will cancel the f of 2. And so on, There'll be an f of n minus 3 here, which will cancel that guy. F of n minus 2 will cancel that guy. F of n minus 1 will cancel that guy. And so, you get a huge collapse on both sides when I add. And what do I end up with? Well, everything canceled, okay, except for the f of n, because there's no, equation above the f of n to cancel with. So the f of n, and what else didn't cancel? All the numbers that I added. So what we conclude, f of n equals 0 plus 1 plus 3 plus 5, and so on, up to what? Up to 2n minus 1. So, conclusion, f of n is equal to 0 plus 1 plus 3 plus 5 plus adding 2 each time plus plus all the way up to 2n minus 1. Okay? So, I don't have a formula for f of n, but at least I have something that's not a recursion. Okay, so this is an example of a sum. We'll deal with sums later. This is the sum of the first n odd numbers, and it's well known that the sum of the first n odd numbers is n squared. Now, if it's not well known to you, forget about that. I'm telling you. Okay. So we had a sum, and if we could compute this sum, you'd find that it's equal to n squared, which we had guessed anyway. So now we are starting to believe our guess. Okay. Because we've sort of derived it with a little bit of monkey business in here, canceling and, pretending that, we can actually add all these together and equate it to all those together, which we can, but, there's a little bit of shady business that went on. Okay? But that's the point. You're allowed to do shady business. You're allowed to tinker around, okay, in coming up with a guess. So I claim this is f of n. Okay? And now let's prove it. And bam! Here comes induction again. Okay. So, if you want to know what function you're computing, you make a guess, you tinker, you unfold the recursion, you make a guess, but to be absolutely certain that your recursion is computing what you think it is computing, and this is very important to prove because as we saw, what can happen when recursions go bad, you prove it with induction. So, claim f of n equals n squared. You could think of that as a predicate. Okay, proof by induction. Okay, now I just want to show you how we prove things by induction when recursions are involved. And the recursion will be instrumental in this proof. And I'm not going to have to compute this sum. Okay, and that's the beauty of the induction. It'll give me a fully 100% hardcore rigorous proof of that fact that this recursion computes n squared without me having to actually compute this sum. And so in this proof will almost be a proof, a derivation of the fact that this sum is n squared. But remember, n squared at the moment is just a guess. Okay, so the proof, base case. When n equals 0, f of n equals 0, which is equal to 0 squared. So check. The base case is true. Now, the induction step. Okay, I need to prove that, that if it's true for n, then it's true for n plus 1. I need to prove that my claim for n implies the claim for n plus 1. So now I'm going to go a little bit more quickly. Okay, so in the induction step, we assume, f of n is equal to n squared. Okay, I'm proving an implication. I get to assume the case for n and now have to prove it for n plus 1. So I need to prove f of n plus 1 equals n plus 1 squared. Remember, f of n plus 1, I replace n with n plus 1. Okay, but what is f of n plus 1? This is where the recursion comes in. Okay? I know that, n is greater equal to 0, so n plus 1 is greater equal to 1, so I can use the recursion. F of n plus 1 is equal to 2n minus 1. Okay, oh, sorry. 2 times the input n plus 1 is equal to 2 times n plus 1 minus 1. Okay, plus f of this thing minus 1. So plus f of n. Okay, so If I plug in n plus 1 into my recursion, I get 2 times n plus 1 minus 1 plus f of n plus 1 minus 1, which is f of n. Okay, I can compute f of n plus 1 if I know how to compute f of n. But by my induction hypothesis, I got to assume, so this is the mechanics of induction, I got to assume that this guy is n squared. Okay, so this is 2, I'll multiply it out, 2n plus 2 minus 1, so that's 2n plus 2 minus 1 plus n squared, which is n squared plus 2n plus 1, which we all know is equal to n plus 1 squared. And there, I've proved it. Okay? That if my claim is true for n, then it's true for n plus 1. So by induction, the claim is true for all n greater or equal to the base case, which is 0. By induction, okay, the claim is true, so f of n equals n squared for all n greater or equal to 0. End of proof. That is a hardcore proof. You can take it to the bank that this recursion computes n squared for all n greater or equal to 0. Okay? So, next we'll talk about recurrences. So let's erase.